Hello everybody, I'm Matteo Busi from the University of Pisa, and today I'm going to talk about comparing fully abstract and robust compilation. This is an ongoing work in collaboration with Carmine Abate from the Max Planck Institute for Security and Privacy, and as the first thing, let's start by taking a closer look at what we mean by fully abstract and robust compilation in our setting. A compiler is said to be fully abstract if it preserves and reflects contextual equivalence. In other words, if we denote a compiler with these two square brackets that you can see here and here, we want to ensure that two source programs P1 and P2 cannot be distinguished by an arbitrary source context, which is how we model attackers, if and only if P1 compiled and P2 compiled cannot be distinguished by an arbitrary target context. Instead, with the term robust compilation, we refer to a family of criteria, some of which are known to be strictly stronger than fully abstract compilation. For the purposes of our work, however, we just focus on the preservation of classes of hyperproperties under adversarial contexts, where an hyperproperty is a set of traces that describes the behavior of a program. More precisely, robust compilation in our setting prescribes that if a source program P robustly satisfies an hyperproperty H, meaning that it satisfies it under any context, then its compiled version satisfies the very same hyperproperty H in an arbitrary target context. So far we have two notions of secure compilation. On the left, you can see fully abstract compilation, and we have preservation and reflection of contextual equivalence. On the right, we have robust compilation, which is the preservation of classes of hyperproperties under adversarial contexts. A natural question is under which conditions fully abstract compilers are also robust compilers. And of course, we are not the first to investigate such a relation. And in particular, it has been shown that in general, fully abstract compilers are not robust, not even if one focuses on specific hyperproperties like no-interference. However, fully abstract compilation has been widely successful for the last 20 years, also when considering the preservation of specific hyperproperties like no-interference. These results together suggest that comparing the two notions just by checking whether one logically implies the other is not completely satisfactory. For that, we propose to investigate a different question. The question we try to answer is, given a fully abstract compiler and a program P that robustly satisfies an hyperproperty H, what is the hyperproperty that is robustly satisfied by the compiled program P? Moreover, under which conditions the hyperproperty that the compiled program satisfies coincide with the original hyperproperty? In fact, in the latter case, a fully abstract compiler is also a robust compiler. So again, let's take a look at our current definitions. On the left we have again fully abstract compilation, and on the right we have again robust compilation. First of all, we can notice that fully abstract compilation talks about contextual equivalence. So the blue relation here and the red relation here, which is a relation between programs that is often defined as equiconvergence or equidivergence. On the other hand, robust compilation focuses on the robust satisfaction of hyperproperties that, as we know, are sets of traces. So for any comparison to be possible, we chose to pick contextual equivalence to be trace equality, which is a possible choice, but we leave different choices as future work. The other issue to be solved is that robust compilation only talks about a given hyperproperty H at the source and requires it to be preserved as is at the target. However, we need a slight generalization of this. In particular, we consider a mapping tau tilde between hyperproperties, and we change robust compilation as follows by requiring that if P robustly satisfies an hyperproperty H, then P compiled must robustly satisfy tau tilde of H. We are now ready to state our preliminary results. The first result is quite interesting. It is possible to prove that a given fully abstract compiler is always, in some sense, a robust compiler. In particular, we can prove that given a fully abstract compiler, it always exists a mapping tau tilde such that if P robustly satisfies an hyperproperty H, then P compiled robustly satisfies tau tilde of H. Also, we can prove that tau tilde is optimal, in the sense that if P robustly satisfies an hyperproperty H prime, if P compiled robustly satisfies an hyperproperty H prime, then tau tilde of H is included in H prime. But there's more. On top of the theorem of the previous slide, a straightforward corollary gives us a sufficient and necessary condition to understand if a given fully abstract compiler robustly preserves a fixed hyperproperty. In principle, it would suffice to decide if tau tilde of H is included in H. However, there is still one big problem, the computation of tau tilde. To see why the computation of tau tilde is a problem, let's see how tau tilde works on a given hyperproperty H. First, it takes all source programs that robustly satisfies H, then it compiles them all, and finally returns as a result the set of their traces in an arbitrary target context. Such information is of course way too much, and much more than just knowing about the preservation of a given hyperproperty for the compiler in hand. Moreover, such a computation highlights the fact that tau tilde actually depends on the compiler itself and on the language we are considering. To fix this issue, in our ongoing work, we are trying to work around this problem by considering successive over or under approximations of tau tilde, depending on what one is willing to prove. So, assume, for instance, that you want to show the preservation of robust non-interference, which we denote here as an I. By the corollary above, this means that if the compiler is fully abstract, it suffices to show that tau tilde of an I is included in an I. For that, we can successively over-approximate tau tilde with a family of mappings, as you can see here, F1, F2, Fn, until it becomes easy to show, or actually maybe trivial, that the over-approximation is included in non-interference. If we are interested instead in showing a violation of non-interference, the corollary requires to show that tau tilde of Ni is not included in Ni. For that, we can try to under-approximate tau tilde until it is clear that its nth under approximation is not included in NI. Though we have not generalized the approach, in the abstract you can find a small example to illustrate this technique. In particular, the example considers a source language in which programs are lists of assignments and all weight-tagged programs are non-interferent. The syntax of the target language coincides with that of the source, but its semantics differs, so breaking the non-interference property in some of the target programs. Now, if we take the identity function as the compiler of interest, we can prove that the compiler is fully abstract according to our definition. So the real question becomes, does it robustly preserve non-interference or not? Well, the answer is no. Since we can prove by computing tau tilde of Ni by successive under approximation and show that at some point the approximation is included in tau tilde of Ni but not in Ni, thus proving that that tau tilde Ni is not included in Ni, and due to our corollary that the identity function does not robustly preserve non-interference in this particular setting. To sum up, we have shown that fully abstract compilation implies some form of robust compilation parameterized by a mapping of hyperproperties called tau tilde. For more details, you can have a look at the appendix of the abstract that was also partially formalized in Coq. In some very particular cases, our choice that contextual equivalence is equal to trace equality follows from determinacy. Our next step is to generalize this result to other notions of contextual equivalence. Another step we plan to make for this work is to provide a general technique of approximating tau tilde that we showed here to be not really computable and to be compiler and language dependent. Finally, since we are particularly interested in non-interference, we want to explore better what happens to non-interference when it is mapped by tau tilde. In particular, our guess is that maybe under some mild assumptions, tau tilde behaves as a declassification of non-interference. And that's it. Thank you for listening. You can find more details about our work on this link on arXiv, and we are happy to take any question or suggestion for this work.